coming back down here after your delightful lunch. So, 3 speakers this afternoon. First 2 are going to plumb the depths of history of science, human psychology, and the normal, aka pseudo-gap state, or marginal state, or strange metal state of the Cuprates. And then the third talk, equally exciting, is on the subject of a novel iron-based superconductor, and that will be after the coffee break. So without further ado, let me hand over to Tony Carrington.
Okay, thanks, James. Let's talk about the normal state. I've noticed that a lot of students here probably didn't live through the early 90s. And so I thought I'd recount some of the story about the normal state of the high-Tc cuprates, and to bring it a bit up to date and show you, well, at least in my view, what our current understanding of all of this is. Now, the first thing is that, this is a conference on superconductivity approaching room temperature. And so the first thing you might ask as a student is, why don't you study the normal state anyway, right? It's not superconducting. Well, the main thing is that on a very simple level, the superconducting state is completely the normal state. It's got a lower energy than the normal state, and that's where it superconducts. So obviously, if you want to understand why the superconducting state is the preferred state, you need to understand what the normal state is in the first place. So what is the superconducting state competing with? Okay, so that's the sort of perhaps most fundamental reason. But actually, by looking at the normal state, you can identify things like what are competing phases. So there are different possible ground states. They're not just normal paramagnetic metal ground states, but they can be other things like charge density waves, spin density waves, or things much more exotic. So what are those competing phases? What are the scattering processes that are involved? So the things which are causing pairing are also scattering in the normal state. So we want to try and identify what those are. And then also, are there more weird things happening? So is the concept of a quasi-particle valid? Right, so you used to sort of, conventional metal physics where we've got Landau Fermi liquid, we've got quasi-particles. They're scattering, but to what extent is actually that valid, right? So, to what extent can you really think about, electrons in that way? There's a question of whether these particles, if they exist, are coherent or not, or should they really be replaced by some effective collective excitation which isn't adiabatically linked to the original electron. Okay, so those are the reasons why you want to study the normal state. So, as I said, we're going to go over a bit of some ancient history. So, since this is really the first talk on Cuprates, I'm going to start off by giving you a brief introduction to Cuprates and a sort of zero-level introduction to the electronic structure. I'm mostly going to talk about the transport properties, in particular the resistivity and Wall effect, and then I'm going to go through just briefly Boltzmann theory. So how do we understand both these resistivity and Wall effect in terms of scattering processes on the Fermi level, and then we'll see to what extent this really explains the behaviour we see. And then finally, I'm going to talk about an overdope cuprate, thallium-201, and that's going to take us through some material on quantum oscillations in cuprates. Okay, so let's just begin by looking at this here phase diagram. So this is a sort of what we deem as a sort of generic phase diagram of cuprates, and just to orientate you, it has its main features. So here we have the number of doped holes. So this isn't the total doping in the system, but it's the number of holes that have been added to what is called the parent material, which is 0 on this scale. So this might be lanthanum copper oxide. And we'll come back to how many holes there really are in a second. Okay, so what's found experimentally is that this thing is an insulating antiferromagnet. So different to in the ion-based case, where it's a metallic antiferromagnet, here it's an insulating antiferromagnet. And as we dope this, the antiferromagnetic ordering temperature falls to 0. In principle, there should be a quantum critical point somewhere there. Whether there is or not is open to conjecture. But anyway, at that point it becomes metallic and a superconductor. And it has this sort of dome of superconductivity with some little nicks in the dome here and there. And there are some competing phases. Okay, so one is called the pseudo-gap phase, and one is a charge density wave. And then right over here, which we call the overdoped regime, there is evidence that the material behaves as a normal Fermi liquid, with some caveats, as we'll come to in a bit. So that's just to sort of show you what the general phase diagram looks like. So, for those of you who've not familiar with the Cuprates, it can seem a little bit like an alphabet soup. So this is just to sort of introduce that there are various different families of Cuprates, and they're distinguished in each family by the number of layers. So for example, if we look at this one, the thallium family, we've got thallium 2201, which has got a single copper oxide layer. The next one up's got 2, and the next one up's got 3. And generally, the TC increases a little bit as you go to more and more layers, but it's roughly about the same. It's roughly always about 100 Kelvin, plus or minus 20–30%. So depending on what your experiment is, you pick one of these as your favourite. Everybody's favourite is YBCO. Well, not everybody. Many people's favourite is YBCO. Right. So this has got a high TC and it's clean. So that's its main unique selling point, as it were. And it's, when we say clean, what we mean, we're talking about disorder in the copper oxygen plane. And the nice thing about this one is that when you want to dope it, the dopants sit away from the plane. Right? So that is true for that one. And it's true for some of the other ones too. So the main ones I'm going to talk about in this talk are YBCO, and I'm also going to talk about this material here, thallium 2201. Now this is a single layer cuprate, and it's almost like the sister of this, except this is not a single layer, it's a double layer, but anyway. There are various other cuprates, as you can see from this, this view graph here. In principle, this one is perhaps one of the simplest. So this is one of the first ones they discovered, lanthanum strontium copper oxide. This is a single layer, and it can be doped over the full range. The only problem is it's not a high TC superconductor. It's only got a TC of about 40 Kelvin. And probably that's due to either strain in the lattice or disorder. Okay, so that's your orientation. Now, when we're looking at these materials, we're thinking about them nowadays in the context of a whole bunch of other materials that have been discovered to be superconducting on the edge of magnetic phases. So heavy fermions, organic superconductors, and more recently these ion-based materials. And what you notice for a lot of these materials is that superconductivity produces this little dome here that's located at the end of this antiferromagnetic phase, in the ion-based and in the heavy fermion materials. In the cuprates, it's not so obvious what that competing phase is, right? So at the end point of this antiferromagnetism, TC is 0, and so people have been looking for other competing phases which have got a quantum critical endpoint which approximately lines up with the maximum in TC. And the contenders for that are this pseudo-gap phase or the charge density wave. Okay, so your basic structure of the cuprates is that we have these copper oxygen planes, and then we have a bunch of other stuff, and the bunch of other stuff basically pulls electrons away from these planes and ends up doping them. And all of the cuprates have this in common, and as I said, in terms of whether they're clean or not, the main thing is how far away the disorder in the doping layer is away from this copper-oxygen layer. Okay, so very basic electronic structure. If you take the parent compound, lanthanum 2, copper oxygen 4, and then you assign some formal valencies to them, so lanthanum is 3 plus, oxygen is 2 minus, and if you add up all of the charges, you work out that copper must be in a 2 plus state, and it's in a tetragonal crystal field, and so the D levels split like this, and you end up with a single unpaired electron in the copper dx squared minus y squared level. And what happens is then that electron in the copper 3D level hybridizes with an electron in the oxygen 2p level and forms a coherent state like that, forms a bond like that. So if you did density functional theory on lanthanum and copper oxide, what you would find is that it's a metal. There's a single band, which is this hybridized oxygen and copper band that's hole-like, and a single band passes through the Fermi level, and then you get a bunch of other stuff here and here that's away from the Fermi level. And the Fermi surface is basically two-dimensional because basically if you look back at the structure, you can easily make electrons move in this direction, but they're very hard to move in this direction, so it's two-dimensional. Okay, so this is what you would get from density functional theory, but as you probably know, it fails. So we know that that lanthanum copper oxide is not a metal, it is in fact an insulator. And the reason it fails is due to Mott-Hubbard physics. So in the standard LDA description, you don't have this fluctuating term here, so this term here fluctuates as a function of time as electrons jump on and off the different sites. And in the LDA approximation, you don't have this term. Okay? So this Mott-Hubbard term splits this band. So in the lanthanum copper oxide, you have 1 electron per site, and therefore it should be a half-filled band and good metal. But in fact, this is split into 2 by the Hubbard U, and you get a completely filled lower Hubbard band and a completely empty upper Hubbard band, and the Fermi level sits in the middle, and it's an insulator. Okay, so that's sort of the very basics. Now, what happens now then, if we take this state and then dope it? Well, we know experimentally that what happens is that we destroy the magnetism and it becomes a metal. So eventually, that probably indicates that this gap must close. So the enduring question is, though, how much Mottness remains in the metallic state? So does this gap close just simply and we just end up back to this situation? Or does it close differently in different directions? Is it fluctuating with time, etc.? And these are some of the enduring questions of this, of how much of this Mott physics is actually relevant in the superconducting state. Okay, so that's a sort of brief introduction to the Cuprates. Now let me get on to the transport properties. Okay, so this really goes back a long way, and back to really at the start of the story. And one of the things, if you ask people what about the transport properties of cuprates, and they'll tell you, oh, they're anomalous. And why are they anomalous? Well, it's got this strange linear resistivity. So let's deal with that first. So what do we mean? So we all know that if you take normal metal, if you're at sufficiently high temperature, the resistivity does vary linearly with temperature, right? So if otherwise you wouldn't have platinum-based thermometers, for example, right? They'd be useless, right? But the point is that in the cuprates, this linearity extends over an extraordinarily long, wide range. Now this is a bit of an extreme example, actually. This is material bismuth, single-layer bismuth 2201. It's a very disordered material that's only got a TC of about 10K. But you can see that the resistance varies linearly all the way pretty much from 0, or just above TC, right up to about 700 or 800 Kelvin. until all of the contacts fall off and the thing sets on fire. So what does that mean? This means that if you think about a general theory where you've got electrons scattering off some bosons, so electron-phonon scattering would be an example. So in electron-phonon scattering, you have an energy scale, and the energy scale is a Debye temperature. And if you're at temperature well below the Debye temperature, you don't get this, right? It's no longer linear in T, right? Because the number of phonon modes, at high temperature, the scattering is basically determined by the number of phonons. And at low temperature, the energy structure of the phonons becomes important. And that would be true for any other scattering mechanism. So this was hailed immediately as a very important result, because it seemed to suggest that whatever the thing was causing this linear resistivity didn't have any intrinsic energy scale. Okay, so I'm embarrassed here to put up some data for my own PhD thesis, but I thought, why the hell not? So this is what happens actually. What I just showed you is for one particular disordered cuprate, what happens sort of more generally. And so this is some data here for YBCO as TC changes. So optimal doping, so with this oxygen deficiency essentially 0, then again it seems to be linear. Okay, it's cut off by the fact that TC is 100 Kelvin, but it seems to be linear and goes through 0 essentially, indicating that, again, that it's got a very low residual resistivity. But as you go away from this optimal doping, the resistivity changes shape, and it adopts this kind of S shape. So we'll come back to that in a minute. The Hall coefficient is also odd. So as you know, that the Hall coefficient in simple metal should just give you 1 over the Hall coefficient, should just be the carrier density. Okay? So in a normal metal, you'd expect the Hall coefficient to vary very little with temperature, basically because the carrier density isn't changing. We'll come to some caveats and to what extent that's true in general later, but generally speaking, that is approximately true. So, but what you find in the cuprates is that this is varying almost linearly with temperature. So 1 over that is varying linearly with temperature. And so you might immediately think, okay, that must mean that the carrier density is changing, right? But like a semiconductor. But we know from other measurements, of optical measurements, but also just from looking at the resistivity, that that's not the case. So if you were immediately losing carriers, you wouldn't expect the system to be metallic. Okay, so you've got these two anomalous properties. So what we've looked at here is what happens at optimal doping and what happens when we underdope. What happens when we overdope? So what happens when we go to the other side of the phase diagram? So the archetypal material to study this is not YBCO, but thallium-2201. And what's found is that the linear resistivity when TC is high gives way to something that varies much more like T squared when TC is very low. The Hall coefficient, on the other hand, starts off being approximately linear with temperature, 1 over RH, and then as you get more and more overdoped, the temperature dependence becomes weaker and weaker. So here it's only varying by about 10% over the full temperature range. Okay, so if we focus now on the resistivity, how should you interpret that data? Well, it's been remarked many times that near a quantum critical point, you might expect there to be a fan of non-Fermi liquid behaviour where the resistivity varies linearly with temperature. So this is what this looks like in the cuprate. So we've actually, this is some data from my colleague Nigel Hussey on lanthanum strontium copper oxides, which can be doped over a large range. And then secondly, the nice thing about this is that you can easily suppress superconductivity with a high magnetic field. And indeed, what you find is that at very high overdoping, you get this T-squared behaviour, and then linear behaviour at optimal doping, but interestingly, the linear behaviour seems to actually extend to low temperature. So it has this kind of shape, it looks like a foot, right, rather than a fan. Okay, and that sort of contrasts a little bit with so the ion-based superconductors. So this is data from Shigeru Kasahara and Yuji Matsuda's group, where they showed that there is indeed this fan of linear resistivity which stems out from the quantum critical point in this material. So this is a sort of a popular way of representing the data by looking at this exponent where rho is t to the alpha. There is another way of looking at the same data which may have more physical relevance, and that is essentially to fit it to combination of t plus t squared. So why that might have more physical relevance is that you could imagine that if you had a situation where you had two different types of carriers, and okay, in principle you should have the conductivities, not the resistivities, but it amounts to a similar thing in this case, is that you could imagine that you've got two different types of carriers, one which is scattering in a certain way, and one which is scattering in another way. Alternatively, you can also think about it on a single band. It's to do with the anisotropy in the scattering, and we'll come back to that later. So if you look at the same data in this way, and you look at the size of this linear term, what you find is that the linear term goes to 0 pretty much right at the edge of the superconducting dome, so about doping of about 0.3, and it increases to a maximum value at optimal doping. So it's as though this linear term correlates with the superconductivity. The emergence of the linear term in the resistivity correlates with the emergence of superconductivity. Okay, so back to the underdoped behaviour for a minute. So I said that this has this kind of an S shape. So the interpretation of what's going on with that is that this is this decrease in the resistivity marks the onset of the so-called pseudo-gap. So what is the pseudo-gap? Well, it's been characterised by a number of different probes, but basically you can think of it as a depression of the density of states near the Fermi level. Okay, so there's some controversy as to whether or not when you get to this point here, T star, so basically just to sort of run you through this, you've got the resistivity, optimal doping, it's linear, and then as we take oxygen out, it's still linear at high temperature, and then at some point it breaks away from it, and we call that T star. Okay, and it turns out that this T star here is an energy scale which is replicated in lots of different experiments. So, for example, you can see a depression of the heat capacity, the gamma, at about the same temperature. The night shift was historically the place where it was identified first. You see a downturn in the night shift. And all of these things seem to determine a common scale. Now there's been some debate over the years as to whether or not this is actually a phase transition or is it just an energy scale. So the distinction is that you could imagine that you've got a depression of the density of states, and it's there, I don't know, up to some very high temperature, but what's happening is that the Fermi window is basically averaged at very high temperature. The Fermi window, the fact it averages over everything. Jorg?
You can finish your sentence, but I have a question.
Oh, sorry. Whereas as the temperature becomes low, then the occupied density of states is focused more around the Fermi level, and so you see more of this depression. So one of the things against this being an actual phase transition is that people have looked very, very carefully, and there is no heat capacity anomaly as you go through this point. However, very recently, Yuji Matsuda's group has identified a change in a thermodynamic quantity, namely the anisotropy of the in-plane torque, which does seem to occur at a similar temperature, but whether or not that truly marks the pseudo-gap or is a consequence of the pseudo-gap forming, I think is still an open question. Jorgen.
Could you go back one step, please? Yes. So there is a lot of discussion, as you're very well aware of the slope of the scattering rate and temperature, Planckian scattering and so forth and so on. I mean, this is the resistivity, not the scattering rate there. But if other things don't change too much, am I supposed to conclude that the coefficient of the scattering rate and temperature is not unity, as many people argue is relevant for this Planckian scattering? Do you know what I'm trying to say?
Yes. So you're saying is if I divide the scattering rate by kVt.
Correct.
Yeah.
Yes. So everybody says that the coefficient is 1. So h bar tau to the minus 1
Okay,
is
so
k Boltzmann t.
So the caveat here, Jorg, is it may depend on how you interpret this. If you interpret this as being a scattering rate on our piece of Fermi surface, for example, then that could be true, right? So it could be that that piece of Fermi surface at the Planckian limit is growing. So if I average it over the whole Fermi surface, the answer is definitely no, right? But if, but the fact, because obviously this is changing. Right?
But another implication of these beautiful data is that we do not have a quantum critical point. We have a quantum critical phase.
Yes, indeed.
Yeah.
Andre.
Since Jörg asked a question. You started by showing us the data which shows linear anti-resistivity up to 1000 Kelvin.
Yes.
Then you switch to a data in the range between 100 and, say, 250 Kelvin. And did this splitting into linear NT and quadratic NT dependence.
Yes.
But my question is about experiment. If you look at temperatures above 250 Kelvin and follow what happens with that linear slope as you increase doping, what happens? I mean that this separation into linear and quadratic behavior shows that at higher temperatures you ought to have quadratic behavior. While originally you had linear behavior up to 1000 Kelvin.
Yeah, okay, but that's only at one particular. So that would be, I mean, if you looked at this plot here, that's what this is saying, right? So you've got this linear exponent that's going up to very high temperature.
So beta is 0 there.
Sorry?
Beta is very small there.
Yes.
But if you go to a region where you're supposed to have T-square behavior, question is if you go to higher temperature, whether you recover exactly the same linear behavior as it had before.
So I haven't showed this, but what's found is that this beta coefficient doesn't change very much as a function of Tc. So as you get to this point here, then effectively it's all T. Okay, so this coefficient doesn't change, and this one does. Okay, so anyway, so back to the Hall coefficient. So we, just to jump back a bit, I told you that there's this linear behavior of the resistivity, and there's also this linear behavior of the inverse Hall coefficient. But as I obtain underdope, this gets less and less temperature dependent, and this develops a strange S shape. And indeed, also in the overdope case, a similar thing happens. So this becomes T squared, and this becomes less temperature dependent. But it was pointed out actually by Photon originally that something that does seem to be more conserved over the whole of the phase diagram, in fact he didn't know that when he made the suggestion, but it was subsequently proved to be true, is the ratio of the resistivity to the Hall coefficient, so the cotangent of the Hall angle. So this is basically, if you, in Drude theory, you would just take the ratio of the Hall coefficient to the resistivity, you'd end up with a quantity which is essentially 1 over omega c tau. So taking omega c out of this, should be telling you just the Hall scattering rate. And what the experiment seems to tell you is that this varies like t squared over most of the phase diagram. Okay, so irrespective of what's happening to the longitudinal scattering rate, the Hall-cut scattering rate varies like t squared. So what that seems to imply is then that there's a different type of scattering which turns up in measurements of the Hall effect, which is different to what occurs in the longitudinal one. Okay, so now we're going to move into a little bit of Boltzmann transport theory to understand, well, to try to see how we can understand what's going on here. So I started off by just writing down the Schottky Chambers true integral formula for the Hall conductivity. So what happens when you apply a magnetic field is that you have a Lorentz force on the electron, and as that's always, the VF is always out this direction, the Lorentz force is always perpendicular to it, so it makes the electron go around the Fermi surface. Okay? So the Schottky formula is a very nice one because it's valid in also low field, but also very high field. And you can understand exactly what's going on here. So what you have is the Fermi velocity in the x direction at some angle on the Fermi surface phi, and then the y component of the Fermi velocity at some angle phi shifted by phi prime. So phi prime is how much we've moved around here with the magnetic field. And then we have this phase factor e to the phi prime over omega c tau, which basically says how much of this do we include in the integral. So if omega c tau is large, then this exponential term very quickly makes this integral converge. And so the first approximation, you can just linearly expand v of y and do the integral. That's what's called the weak field limit. And we'll get onto the high field limit in a minute. Now. My computer suddenly decided to go. Okay, so that's the expression for the Hall conductivity. To get the longitudinal one, you simply replace the y here with an x. This will give you the longitudinal conductivity, the magnetoresistance. And then to calculate in 2 dimensions at least, the Hall coefficient, you just take the ratio of sigma xy over sigma xx squared plus sigma xy squared. And the resistivity is the same but with sigma xx on the top. Okay, so that's how you do things in general, but in fact, Farnham showed back in 1991 a very nice geometrical interpretation of the weak field Hall coefficient. So this is the Hall coefficient in the limit that the field tends to 0. Okay, so the construction that he used was this, that if you take a Fermi surface and just take for the sake of an example, one that's kind of square but with rounded corners, which by coincidence looks a little bit like Cuprates, but it serves as an illustration anyway. Okay, and then as we go around the Fermi surface, we have a mean free path wave vector. So this is just VF times the scattering rate, so L. Okay, and you can see that, you know, here VF is always going to be perpendicular to the Fermi surface, so here it points in this direction, here it points in this direction, and here it points in the 45-degree direction. And then what you do is then you map out what happens to this L vector as you move around the Fermi surface. Okay, so here we'd start off right here, and we'd stay there all the way until we get to right about this point here, at which point we go around here, and then end up back here again. So we trace out this curve. Now in general, this could trace out quite a complicated curve. It can trace out a curve that's got multiple loops in it, but I'll just take a simple example here. Then Ohm showed that the Hall conductivity, sigma xy, is simply the magnetic field times the area traced out by this L loop divided by the flux quantum times the quantum of conductance. So it's a very simple geometrical way of looking at the Hall conductivity. And what you can see then is that sigma xy is dominated by what happens round about these corner regions. So what happens here is kind of fairly irrelevant. It's what happens here that matters. That's the thing that's going to determine this area. On the other hand, the longitudinal resistivity, sigma xx, that just depends on pretty much a straight average of L around the Fermi surface. So it's essentially just S, which is kind of the length around the Fermi surface, times some average of the mean free path. So, where are we going here? Sorry. So what this shows you then is that, in general, the Hall coefficient is not going to give you exactly 1 over ME. What it's going to give you is a number which could be larger or less than 1 over ME, and the degree to which it does so depends on how the mean free path varies as you go around the Fermi surface. And mostly the response is always going to be dominated by the regions where there's large curvature, so the corners in the Fermi surface like this. Okay, so what has theory come up with for these experimental facts? So, sorry, I've just given you some background in Boltzmann theory. So what have we got to explain that we seem to have these different lifetimes? So optimal doping, you would say that you've got a scattering which determines the resistivity, which is linear in temperature, whereas the scattering that determines the Hall coefficient goes like t squared. Now the original suggestion of what was going on here was due to Phil Anderson back in the very early 90s, where this was, for him, the smoking gun for his spin-charged separation picture. So he had not electrons, but collective excitations of the system, which were these holons and spin-ons, and these had different scattering rates. So essentially, you had a kind of a two-fluid, and the holons and the spin-ons either reacted differently to magnetic field, and that gave rise to these two scattering rates. Recently, this kind of two-fluid picture has been reinvented in a different guise. So this is the guise of holographic metals. So this is a theory of what you might expect in a quantum critical regime, based on analysis of black holes. And in this case, Blake and Donos showed that, again, you've got these essentially two different origins of currents, and they react differently to magnetic field and longitudinal electric fields. On a more sort of vanilla basis, based on this sort of picture, you can also, to some extent, explain what's going on just using anisotropic scattering. Right, so you've basically got a Fermi surface, and then you've got a scattering rate which varies around the Fermi surface, and this fact that the scattering rate, the Hall coefficient, is dominated by the bits on the corner, you can exploit by making the scattering rate on the corner go like t squared, and the scattering rate on the flat bits go like t. Now, does this work? So this was originally, well, as far as I'm aware, proposed by John Cooper back in the early 90s, and it kind of works, but only if you really tweak the parameters, right? So you can get it to work, but it's very unlikely, in my view, that it's the definite the explanation, because it only works for very particular parameter sets. Okay, we'll get into that. Okay, so just for completeness. Since we're going to go in a minute to what happens in high field, I thought I'd just point out what happens when you've got two bands. So in Cuprates, generally you've got one band physics, But if you've got two bands, which you have to have in ion-based superconductors, for example, then what you have to do is to add the conductivities, both the Hall and the longitudinal, from the two different bands. So you add the conductivity tensors, and that gives rise to these rather complicated expressions for the Hall coefficient and the resistivity. So if you start off with a model where the Hall coefficient is independent of field, and the magnetoresistance resistance is negligibly small, then when you combine the two bands, you end up with the Hall coefficient that now is dependent on field, and a resistivity that also is dependent on field. So often then people then talk about the weak field and high field regime of this expression. So that's going to be different to what I'm going to be talking about in a minute, which is when we're really going to go to the high field regime, where we only can see tau is much greater than 1, or avoid 1. Okay, so where two bands actually do come into things in the cuprates is in the compound YBCO. So although this is, you know, in many ways one of our favourites, it has this horrible complication that it has our nice copper oxygen planes, but it's got these oxygen deficient planes, which we call chains. So they're missing an oxygen here and here, and they give you one-dimensional structures, which on the Fermi surface, a DFT Fermi surface, give you these bands here, and you can see these bands actually cut across the planar band. So we've got two planes. So we've got these are the two copper oxygen plane bands, and the chain band cuts across them and hybridizes with them. Now, within an approximation, and the approximation is that you have isotropic mean-free path, you can show that the Hall conductivity from a one-dimensional Fermi surface, if you've got isotropic mean-free path, is exactly 0. Right? So basically, if you look at, this is actually a figure from Ong's original article. This is a quasi-one-dimensional Fermi surface. It traces out this kind of banana shape like this, but you also trace out a banana shape of the opposite circulation from the other band, and the two things cancel out to give you 0 area, and so that the Hall conductivity is exactly 0. So therefore, if we look at YBCO, then we would expect there to be a response to the chains and a strong response to the planes, and we should add the conductivities together. But we know that this one should be 0, and in the x direction, there's no contribution from the chains. So this is the x direction, so we get a contribution in that direction because there's this quasi-one-dimensional Fermi surface gives rise to currents moving that way, but not that way. So you cross these two out, and then with a small bit of mathematics, you can show then that the Hall coefficient that you measure is essentially related to the one that you would get if you didn't have the chains, multiplied by the ratio of the resistivity along B divided by the resistivity along A. And you can kind of understand this. Basically what it's saying is that if you put the current along the x direction, some of the current's been taken up by the chains, but it hasn't got a Hall response. Okay. Right, so let's move to what happens in high field. So in high field, we now, the quasi-particles go a long way around the Fermi surface, and in the limit that this becomes much greater than 1, then essentially you average over all the anisotropy in the scattering rate and the mean-free path, and you get some bits where it's higher and some bits where it's lower, and then because the integral goes all the way around the Fermi surface, sometimes many times, this ends up that the Hall coefficient goes back to being 1 over ME. So that means that in the high field limit, all of this business with the scattering rate anisotropy should be irrelevant, and you should go back to it equaling exactly 1 over ME. Okay, so some experimental data. So there's this very important paper from 2006 by Sven Baidu and Louis Taillefer, and they showed that if you took YBCO and you measured the Hall coefficient and you tried to go to the highest possible field and the lowest possible temperature, you should be recovering the Fermi volume, so 1 over ME. And what they found was that there's this abrupt rise in, this is the Hall number, so this is basically 1 over ME, 1 over RHE, and there's this abrupt rise. And so the interpretation of this was then that what this signifies is that at P star, which is the pseudo-gap point where the pseudo-gap starts, that there's some change in the shape of the Fermi surface at t equals 0. Right? So the implication is that the Fermi surface goes from being a big Fermi surface to something that's got small pockets, such that the carrier density is much smaller. So instead of being 1.2, it's 0.2. So it reduces by about a factor of 5. Okay, but there's a couple of caveats here. One is, how do the chains influence things? Right? Because we know here that the measured Hall coefficient is actually reduced. The measured Hall coefficient is increased, or the Hall number is reduced due to the presence of the chains. And secondly, what happens when you're really over here? So in this plot here, there's this one point here, thallium 2201. So we're interested to know what happens in the intermediate regime. Okay, so here we go. We're on to thallium 2201. We've already said that the resistivity evolves from being linear in T to going like T squared. And importantly, when it's very overdoped, the mean free path is very long. It approaches 1,000 anetrons. Resistivity is a few microamp centimeters. It's only got a single layer, it's electronically clean, it's a single band, there doesn't appear to be any Lifshitz transitions, and importantly, there's no evidence whatsoever for a pseudo-gap. Okay, so what do we know already? We know from analysing angle-dependent magnetoresistance roughly what the shape of the Fermi surface is, and in the interest of time, I'll zip on to quantum oscillations. So in 2008, we observed quantum oscillations for the first time, which showed that there is a large Fermi surface with that filled was essentially had the volume of what we'd expect, so 1 plus p volume. And we then took this and tried to, we first of all discovered quantum oscillations with a very overdoped sample of TC of 10K. And then we spent a long time, many years, trying to find quantum oscillations in higher and higher TCs. I think we measured something like 60 or 70 samples in pulsed field in the end. And we found success only at 26 Kelvin. That was the highest TC we ever saw quantum oscillations in. Okay, so keep that number in mind for later. Interestingly, actually, if you compare the data for the 10K and the 26K, it's not actually significantly different in terms of amplitude, given the fact that there's often these exponential damping factors. Okay, so what do we know? Now we know in quantum oscillations, we can measure the effective mass. We know exactly what the doping is, it was 0.3. You can find the effective mass, you find the normalizations about a factor of 3. And then by looking at the amplitude and how the amplitude varies as a function of the field angle, you can work out exactly all of the little wiggles and wobbles in the Fermi surface. You can expand the shape in terms of these cylindrical harmonics. We can fit the DFT calculation, and then we can compare these numbers to what we actually measure. And they're in extremely good agreement. Given the fact that, how small these warpings are, you're looking at 1 part in 1,000 here compared to the main warping, and I'd say that's pretty good agreement all in all. Okay, so I'll flash up here some heat capacity data. So there's been a lot of talk about quantum critical points in overdoped Cuprates, and this is a bit of data that nobody likes to show. And the reason is because this is data from John Lauren. It shows overdoped thallium 2201, and what you can see here is that gamma, for all of these different TCs, is almost completely independent of doping. It doesn't change, right? And if you don't believe John Lauren's data, because you say, okay, has this attractive phonons right, or something like that, at least for the most overdoped case, we can make a direct comparison between the gamma that he measures here from heat capacity and the mass that we measure in quantum oscillations. And they're in excellent agreement, as you can see. And that means there are no missing Fermi surface sheets and nothing crazy is going on at all, and that these numbers are right. Okay, but the other thing I wanted to point out here is there's no pseudo-gap. Gamma is constant as a function of temperature. Okay, so, okay, I've got 5 minutes left. One thing we found out from angle-dependent magnetoresistance measurements was that not only could you work out what the shape of the Fermi surface was, but you could also work out what was happening to the scattering. So you could only model the magnetoresistance if you had 2 bits to the scattering. One which was, well, basically the scattering was anisotropic, and this anisotropy changes with temperature. And you could sort of model it as being a component that's isotropic, and the isotropic part varies like t squared, and the coefficient of this t squared doesn't vary with t. And then you've got an anisotropic part, which varies linearly with t and scales linearly with tc. Okay? Now that you know the form of the Fermi surface, the form of the scattering rate, can you explain the Hall coefficient? Answer, yes. So this is that simulation of the Hall coefficient and the in-plane resistivity using those parameters. And you can see it works pretty well. On the other hand, we should say things that don't work as well. It works very well when they're very overdoped, but when the doping gets towards optimal, it doesn't work, right? So this is what you get from the simulation. Notice the scale here. It's only varying by about 20%, whereas the real data is varying by a factor of 2. So the scattering rate anisotropy works to some extent, but it doesn't explain the whole thing. Okay, so what happens at high field? Okay, at high field, what you find is that the Hall coefficient is field dependent. So this is a simulation up to 100 Tesla. And essentially, as you'd expect, as you get to higher and higher fields, you asymptotically approach 1 over NE. Okay? So these are values in simulation exactly for thallium-221. And indeed, that is exactly what you find in the experiment. So this is experimental data up to 60 Tesla, thallium-221. What you find is that this increase, so sorry, I missed off the line here, but this line is this line here. So there's this line of, this should be the carrier density, 1 plus P. And you can see that at high enough field and low enough temperature, it asymptotically approaches that. Okay, but when we repeated this for other dopings, what we found was this. We found that we don't see an abrupt change at 0.19, but rather a very slow change that occurs over quite a large proportion of the phase diagram. And it only really reaches 1 plus P right at the edge of the superconducting dome. In fact, in exactly the same region where we can see quantum oscillations. So this yellow region is where quantum oscillations you can see. This is where the Hall coefficient 1 over n, the Hall number equals 1 over NE, and then it quickly falls here. So this therefore calls into questions whether or not this rise in the Hall coefficient that was reported in YBCO is really linked to the pseudo-gap, because here there is no pseudo-gap. What it does seem to be correlated with is this linear coefficient in the resistivity. So this decrease and this increase seem to both be correlated with the increase in TC as you move away from the superconducting dome. And I'll just flash up some, this is some data for a lanthanum doped bismuth 221, which shows exactly the same thing. Okay, so what does this all mean? Well, it means that this rise of the Hall number isn't linked to the pseudo-gap because we don't have pseudo-gap. It's probably not linked to anisotropic scattering because 60, 70 Tesla should quench this effect. Density wave possibly could explain it, but again, there's absolutely no evidence for this. And what we're really left with is that actually this is a mark of the non-Fermi liquid nature, the non-Boltzmann transport nature of the charge transport in the Cuprates, which seems to extend almost all the way to the edge of the superconducting dome. And I think at that point I'm going to stop. Thank you.
Okay, great.
If I got the statement the right way around, the correction, if you will, that you're proposing that we need to take for the YBCO Hall data would bring that YBCO data down further, as you see in that.
I didn't put it on because it's a bit incendiary, but if you did, the YBCO data sits on that one. But you see, the problem is actually with YBCO, you don't actually know what that ratio is. You know it's around 1.5 at a certain doping, but no one's really done a systematic study to show what that is at low enough temperature in high field. But it's a substantial correction anyway. It's not inconsistent. Amalia.
So the way you extract this number is extrapolating to the highest field possible, is that right? The value of the RH.
Okay, I didn't quite have time to go into all of that, but essentially what you're doing is, no, you're not extrapolating, you're extrapolating to
because the slope changes in field significantly, so I wonder if the slope is telling you something.
Sorry, let me just answer your question. I'll try to find the plot, which is evading it. Okay, here. So this is a simulation actually. So what it's showing is the if you had the values of thallium-201, what the tube integral formula would tell you would happen as a function of field. Right? So you've got this field dependence, but of course you can't extrapolate to infinite field. So what you have to do is to use high field but also low temperature. Right? And the combination of the two is what you use to try and find what the limit is.
But in magnetic field, the slope changes significantly. Does that?
So that, yeah. So that's what I tried to show. Which now, sorry, I've got here. Okay. So you've got this slope, but as you go to low enough temperature, it becomes flat. So at low temperature, you've essentially got isotropic scattering again. So you've got two things which are helping you. You've got the scattering is becoming more isotropic because the temperature-dependent parts have gone. And the second thing is you've got high omega C tau, which is averaging it all out anyway. So you need both things which effectively help you get the T to zero limit. But if I'm sorry, if I like to be honest about all these things. And with this data and the YBCO data, there's always the question: have you really reached the infinite field limit? Right? And we can never really truly answer that question unless we have 1,000 Tesla.
If I may return back to the same questions that I asked you, because you again showed this formula, just from purely experimental perspective. I think there's two ways to interpret or fit experimental data on resistivity. One is by a single formula, which interpolates between T squared at very low temperature and then crosses over to linear NT at higher temperature, and then depending on doping, you change this crossover temperature. Or by just two independent linear NT and quadratic NT parts. Experimentally, can you distinguish between the two?
No.
That was a pure answer.
I agree.
Wait.
I'd like to understand the plot that you have up
Me
here
too.
better. So let's discuss what happens to the resistivity exponent, T to the alpha. In the yellow region where you see 1 plus P large Fermi surface, quantum oscillations, the resistivity is T squared.
Yeah, so that's what this is. So I haven't showed this, but if you were to plot the T squared component, it would be independent of TC.
Okay, and as soon as you start deviating from the 1 plus t line,
Yeah.
The exponent goes from t squared to t.
Well, gradually. So you could say that you've got this linear term that's increasing.
Okay.
With the t
And
squared.
by the time you hit the line nh equals p, it's basically t.
Correct.
Okay, so that's about the resistivity. Now let's go to the cotangent of the Hall angle.
Yes.
Across this entire p doping, the cotangent of the Hall angle continues to be t squared
Correct.
everywhere, including the yellow region?
Yes.
Okay, thank you.
These are concise answers.
They were well-formed questions.
Can I,
Simple yes, no answer.
can I suggest, so after you showed us this beautiful sequence of studies, in conclusion, you said that there's no charge density wave, which certainly is a perfectly valid thing to say for thallium-2201. But I think there's tons of evidence for a charge density wave in bismuth-2201 from
Yes.
dozens of groups.
True.
So there is a CDW on the right-hand side.
Yes. But I just as a, okay, CDWs can do strange things, and it depends on exactly how it reforms the Fermi surface. But in the underdose case, it does the opposite to this. So CDW would make the Hall coefficient change, well, in the underdose case, it makes the Hall coefficient change sign, which means that RH tends to 0, which means that this tends to infinity. So it doesn't make it go down, it makes it go up.
I understand.
But in principle, all manner of reconstructions are possible.
So as a follow-up, where is the CDW regime in the bismuth 2201 slot?
It's in the window where it's sloping up. I mean, it starts over on the left at low doping. It's decaying in its intensity as a function of increasing P, and you have lots of disorder, so you can't say it exists at 1 P and it disappears at another P. It's patchy.
You can see,
But it's gone by the time you get to 1 plus P.
there are people that claim that there's also a patch over here. I mean, the bismuth 2201, you can quite clearly identify, from resistivity anyway, pseudo-gap. And that's why this is
I agree.
0.19.
There's a pseudo.
Yeah, I need to come back, unfortunately, to my earlier question, because
Sure.
your answer, as clear as it was to Andre, confused me.
All right.
So my question earlier was, it is not a quantum critical point, it's a phase, because you have an extended regime in parameter space where you have a non-Fermi liquid temperature dependent of the resistivity. At lowest temperature, the linear T term dominates, it's a non-Fermi liquid phase. When Andre asked, you said, can you distinguish whether there is an initial T squared behavior that then eventually crosses over into a linear temperature behavior? You said you cannot distinguish. So just for me to get the lesson, is there or is there not a quantum critical point, or is there a quantum critical phase to your best judgment?
Yes.
I apologize for the question.
Forensic examination.
Okay, so
So we have only 60 seconds left. So
all right, let me see if I can come up with a coherent answer in that time. Well, first of all, you know, can we distinguish between something that's smoothly going from t squared to t, as opposed to just being t squared plus t? That's experimentally quite a tricky thing to do, especially if it's in high magnetic field. Right, so I think that's a true statement. You're now putting an interpretation on that, and then asking whether or not we can really say whether there's a quantum critical point or not.
Well, I just want to know which fit is the best.
Well, I mean, my view.
okay, I think we should finish this question
Okay.
offline, because now we need to turn. Thank you, Tony.
Okay,
Now we
thank you.
turn to